Hello, everybody. Welcome to the lecture in downstream processing in biotechnology again. For this case, we also will continue on the crystallization process. Previous lecture, we talked about the nucleation kinetic, but for this lecture, we will focus on the growth kinetic. The first kinetic, that is nucleation. After the nucleation, we get the small crystal, and this mostly in industrial application. We would like to control the crystal to be the same size or the size with a uniformity of the crystal size. The technique to control the crystal size, we call it the crystal growth. Crystal growth means the grow the crystal to the larger size. For this case, we have two steps. We talk about the mass transfer. Have two steps. Okay. We have the crystal in solid form and solution in liquid form. In solution, this include two components in solution is solvent and solute in the liquid form. If we operate at the metastable zone or the supersaturation at the metastable zone or metastable zone, we can add, you remember that we have truth. As we have undersat for undersaturated solution that it cannot crystallize, and also supersaturation. Supersaturation we separate into zone. Labile zone is very high concentration that get for the nucleation. And the second zone is metastable zone, the zone that close to the solubility or the sat zone. For this case, it driving force is not high enough to induce the new crystal. But for this case, we can induce the crystallization by crystal growth. Right? We have to see the crystal. Okay. At this operation, in the solution, we contain two forms, crystal in solid form and liquid, right? Or the solution in liquid form. For this case, the solute that's also in supersaturated solute in solvent will be transformed to the crystal sulfate and then make the crystal to be the larger size. For this case, we assume right the bulk solution or the solution allow the crystal. The solution allow the crystal. And so also like the stagnant film or the film allow the crystal surface. It's mostly if we have like the crystal flow in liquid phase. There are some small thickness of the liquid film allow the solid. As mean the solute will diffuse to the film. That's why the diffusion of solute to the interface between film and bulk solution, and then also diffusion to the film and then to the layer of the crystal. For this case, after the layer of crystal, the some solvent or solute molecule will be the integration to be at the king side or the surface that is better to stay. That, for example, okay, this is the molecule of solute in the bulk solution, and then diffuse to the interface between film and bulk solution, and then diffuse further to the crystal surface, this molecule, and then we integrate or change or move to the surface that is the stable. For this case, we surface to this in the edge of something like this. Is the diffusion or mass transfer from the bulk to the film, and then integration of the molecule into the king side, something like this. We have two steps for the crystal growth, the mass transfer and integration step. We call it the integration step. Nice. Mostly we can express the nucleation or the growth of crystal growth in terms of G. G is the growth rate or linear growth rate is the change of the size of the crystal with respect to time. And also we can express the growth rate in terms of mass deposition rate or mass growth rate. Mass deposition means the amount of mass that's accumulate or attached to the crystal surface. We can express Rg, growth rate in terms of mass deposition, equal to dmc by dt. Dmc means mass of crystal, equal to 3 log kV L square. Log kV is the shape, volume shape factor, dl by dt. This is linear correlate. That's a linear correlate. That means Ig equal to 3 log kV L square G. For L square equal to AC divided by Ka. Is the surface area of crystal area divided by area shape factor. And also you can express G in terms of area shape factor and volume shape factor. We call this is the delta law or delta law. The law is the irreducible generalization for an industrial crystallization. We have at least two crystallization site in the site dependent growth. For this case, different site, the correlate is different. Different site, the correlate is different. For that case, usually large crystal growing more rapidly than small crystal, and the rate of crystal growth of crystal is the same, irrespective for the site. This is the site dependent growth, and also we have the site independent growth. Site independent growth means different site keep the same crystal growth. For this is growth dispersion. Growth dispersion means the crystal of the same site grow at differently. This is the growth dispersion, the same site but grow differently. Okay. This is gives you an example of the growth rate of the bioproduct molecule, for example, L-asparagine monohydrate. Growth at temperature of 36 degrees Celsius with the supersaturation of 1.19. This is the relative supersaturation is equal to C divided by C star. As I talked to you for the last two lectures, relative supersaturation sigma equal to S minus 1. S equal to C divided by C star. If the S is greater than 1, that means the crystallization can occur. It may be by growth or by nucleation mechanism. And this is another citric acid monohydrate, glycine, L-histidine. This is the example of the nucleation of the bioproduct. And the theory that describes the growth is mostly we talk about the nucleation. We talk about the mass transfer for diffusion integration theory. For this case, we have two steps, the diffusion and integration step. The first step with diffusion is where the transfer of molecule of solute from the bulk solution to the crystal surface. And the second step is the insertion of the molecule into the surface. Okay, the combine of the kinetic of this process we can represent by Rg. Rg from previous equation. Rg equal to Kgm minus C star power G. Rg is mass growth rate. Km is overall growth rate coefficient, but depend on the system, depend on the temperature, aggregation speed, depend on the physical property of fluid, and also the presence of impurity. And AC is the crystal surface, G is the growth order. We can express the Rg as a function of this is the combined mass transfer and integration step. You substitute Ag equal to this, and then you can solve for G equal to this term, and then we combine this term into KGL. KGL is overall growth rate coefficient. That means G equal to KGL delta C power G. It looks like the power law model of the nucleation. Okay. Mostly we use the crystal code to control the crystal size. Mostly we would like to produce a narrow distribution of the crystal size. Nucleation should be minimized while a relatively rapid rate of the crystal code is maintained. Okay. To provide the better control over the crystal size distribution, we have to add a small crystal add to the crystallizer. Okay, this is the same. Sorry. Okay, this is so you conclude about the interaction between the crystallizer parameter that we have the feed. The feed should be supersaturation, or if the feed is not supersaturation, like if you feed in undersat, you have to create supersat. The simple you can decrease the temperature until it reaches supersaturation. And then we have two kinetic nucleation rate and growth rate. nucleation and growth rate. So mostly the growth rate, it affect the surface of crystal. We talk about the surface of crystal for the growth rate. So you diffuse to the surface of crystal and then go to the dark side. This affect the crystal growth and also affect the supersaturation. And the nucleation rate, we talk about the number of crystal. Number of crystal. This is depend on the crystal mass concentration on the secondary nucleation rate. Also affect the nucleation. And then you get the product. Right. This is show you an example of the growth rate of L-glutamic acid. L-glutamic acid. This is the growth rate in the size per hour, size per time, millimeters per hour. This is the concentration. We can see that at concentration increase, the growth rate is decreased for this. Growth rate is decreased for this. Okay, how to measure the growth rate? There are lots of techniques to measure the growth rate. The first technique for this case, we kinetic, we by see it that the supersaturation. The supersaturation, what does it mean? Supersaturation is the concentration that is higher than solubility. For the supersaturation, the concentration of decrease, level of supersaturation is decreased with respect to time for this case. What does it mean? We have the control the temperature at fixed temperature at maybe 10 degrees Celsius, 25 degrees Celsius, 40 degrees Celsius in the crystallizer. But in fixed, if you would like to study at 10, you prepare the supersaturation at 10 degrees Celsius. Is maybe you heat up at higher than 10 degrees Celsius. And then you reduce the temperature to 10. You add some seed. And then you proceed the crystallizer by mixing. And then you sampling solution and crystal by filter. The solution, you measure the concentration, crystal, you measure the size. And then you will, the conclusion of the function, dissolve some amount of solute in solvent. In solvent, and then you can dissolve at higher temperature. Is for this is about 20% above the T growth. That means the experimental temperature. After it dissolving, we get the clear solution. And then you decrease the temperature to 20 degrees Celsius. 20 degrees Celsius. For that case, you get supersaturated solution, and then you see crystal. You get the process of the crystal growth. And then during this, you sampling the sample. So you measure the sampling the sample, the liquid, to measure the concentration. You can measure by FBIM, by reflectometer, or evaporative to dynamic, or Raman. We have a lot of technique. And also solid, you measure the particle size. It may be by FBIM microscope or PUM that I talked to you previously. And then for this case, we measure the concentration and size with respect to time, at time interval. We have to, and then we plot. This is the supersaturation. We can plot the concentration in terms of supersaturation. For it, we talk about the relative supersaturation. You can see that the relative supersaturation is reduced with respect to time and until it is constant. At this constant, it is the concentration at solubility, and this means sigma equal to 0. At sigma equal to 0, that means C equal to C star. That's right, C equal to C star. That means all of the solute is crystallized. That's all of the solute, the delta C, that's right, amount of solute that crystallized is already, because it's C minus delta C, C minus C star. And in the same way, crystal size. When the solute from the solution diffuse to the crystal, solute in the solution is reduced, amount is a concentration reduced. Another way, size of the crystal is increased. It increased because they have the solute from solution transferred to the surface of crystal. The crystal is increased in size. For this case, we talk with the supersaturation because the supersaturation is decreased with respect to time. Because it's the supersaturation technique. Okay, for this case, you know the equation for sigma as a function of time. equation for linear size, average size, average size with respect to time. And then you can calculate G or average G. Average growth rate is the diff L by dt. You dip this equation by dt, you get this. This is the growth rate with respect to time. And then you can plot the mean growth rate with supersaturation. The mean growth rate you calculate from this equation. And supersaturation you calculate for this equation. Okay, you substitute time, the same time, you get supersat. A supersat, you get an equation growth rate. Did it show you like the growth rate is a function of supersaturation or growth rate is a function of concentration? Okay, for the next, we will talk about the equipment that used in the crystallizer. Mostly in the crystallizer, after you crystallize, you have more equipment to separate. We call it separate unit, mode is centrifugation or filtration to separate solid from the liquid. In the crystallization unit, we have the feed or inflow solution and crystal. It may be only solution, it may be crystal for growth, feed to the crystallization unit. In crystallization unit, it may be some non-solvent or solvent feed to the crystallizer to induce the crystallization by entire solvent crystallization. If we have some vapor, we can push out, and also we have some heat, evaporation you heat in, cooling you heat out from the system, and out for solution and crystal, and separate. You get crystal product as product, and also you sometimes recycle crystal to the feed, and maybe you can recycle solution in the crystallizer unit. After phase separation, we have solid and liquid. The liquid is spent out, something like it. It's more so you can recycle solid liquid to the disk for recrystallization again. You can do that. Right. The next, we talk about the type of crystallizer. We have at least two kinds of crystallization operation: continuous operation and batch operation. The continuous operation, we call it steady state crystallizer. The mass flow rate of the inflow stream equal to the outflow stream. Flow in equal to flow out. That means there is no time variation in any of crystal. That means crystal size in the crystallizer equal to the crystal size in the output as product. Concentration in the crystallizer equal to concentration in the output of the product. That's it. This is the continuous operation. How about the batch operation? For the batch operation, there is no inflow or outflow stream. For this we call this mode. There are no inflow and outflow stream. We call this batch mode. Or sometimes we call this semi-batch. Only inflow or only outflow stream. We call it semi-batch mode. For this case, the crystallizer size, crystal size, concentration of solute inside the crystallizer is very with time. It's very with time. And another kind of crystallizer, we call this seed crystallizer. We have to like seed and unseed. Seed means we like to grow the crystal to be the largest size. For this case, we add some crystal into the clear solution to make it bigger size, And another type of crystallizer we call cooling. We talked this in detail already. It's like we start from underset, and then you decrease temperature and to lead the saturation and decrease faster to create a supersaturation, and then you can crystallize. And the second type of crystallization is evaporative crystallization. For this case, we can generate the supersaturated solution by evaporation out of solvent. For this case, we can evaporate solvent out. If you evaporate solvent out, the solute concentration will increase because mostly the solute concentration is equal to amount of solute divided amount of solvent plus solute. If amount of solvent is decreased, concentration is increased until it leads to supersaturation. For the supersaturation, we can generate or induce the crystallization. This is the evaporation crystallization. And vacuum crystallization. Vacuum crystallization is also mixture of cooling and evaporation crystallization. For this case, we would like to crystallization at lower temperature and lower pressure, because if you induce or reduce the pressure below the atmospheric, the solvent can evaporate at lower temperature. For that case, if the solution is evaporated, and also the solution is cooled simultaneously by decreasing the temperature and pressure. You can get the supersaturation by cooling and heating and cooling, right, for this case. And anti-solvent, or we call this doubting out crystallization. For this case, the crystallization can induce by increase the supersaturation by adding some solvent. We adding another solvent. For example, we have the protein or amino acid dissolved in water. And then you can add some another solvent. Another solvent, this should be preferred to the solvent, not solute. That means it's difficult to dissolve solute, but it's easy to dissolve in our own solvent. That means for this case, if you add some solvent, the solubility of solute in an own solvent is reduced. This makes the supersaturation. Okay. And the last one, the reactive crystallization, work on with the precipitation. Reactive crystallization is the crystallization which we have new chemical or new subject. We add some reactant, react together, and then you get the new chemical, and also we crystallize the crystal from the crystallization. For this case, we can, the crystallization is maybe like homogeneous reaction crystallization and heterogeneous reaction crystallization. For homogeneous, mostly liquid phase crystallization, and heterogeneous mostly we add some gas or vapor form. We have the liquid phase, and then you add gas phase or vapor phase to the crystallizer, and then we add a reaction to produce the crystal and new chemical. And homogeneous phase means we add some liquid phase to the liquid phase. We get the reaction, we get a new crystal and a new chemical like crystal, something like this. And the last topic for this lecture, in this section, we talk about the equipment. For this case, show you 3 types of crystallizer. For the first one is stirrer tank reactor or stirrer tank crystallizer. For this case, we have the stirrer. We feed at this stirrer. And also the product is removed at this point. And also some like the evaporator, right? Some evaporation, some vapor flow out at this. And also some overflow or some fine chemical flow in. In this case, another crystallizer, we feed at this here, at this, and also the solution or motor liquor for downward mixture with the feed, and the recycled solution is sent to the heat exchanger, this is the outside heat exchanger, to heat up or cooling. For this case, we use the exchanger to heat or cool to generate the supersaturation. It's maybe by cooling crystallization or by evaporation crystallization. Until the solution is supersaturated, it's sent to the crystallizer. The crystal is formed and flow downward, or maybe flow downward. The crystal and solution is flow downward, mixed to phase feed, and the crystal can move out by the crystallizer, and some vapor move out at the top. This is also like the same operation, the outside heat exchanger to heat or cool the solution, The feed to the system, mix to the overflow from the crystallizer. Overflow from the crystallizer is more, this is the fine crystal or small crystal. We recycle the small crystal to make the feed and dissolve again. Dissolve and then make the supersaturation and send to the crystallizer. This evaporator, the crystal is moved out here. And this is the cooling crystallizer. The cooling crystallizer, we feed the solution here. And also we pump to the heat exchanger to cool down the temperature until it leads to supersaturation. We send the supersaturation in the crystallizer, and then we move out the crystal and the solution. This is your evaporative crystallizer. We feed the solution mix to the recycled solution and then pump to the heat exchanger. For this heat exchanger, we use the steam because the steam is higher temperature. That means we evaporate the solvent. The solvent evaporate out. Crystallizer include the supersaturation. It can generate or induce the crystal. This is the vacuum crystallizer. Vacuum crystallizer. We have the feed solution here and pump to the pump for vacuum. That's Crystallization. The crystal out here. This is also drop tube crystallizer. For this case, we have the classification. The feed solution feed in like this, and then the drop tube to produce the circulation. If the overhead is evaporative, there are some vapor here, and the crystal is circulation in this zone. The crystal is circulating in this zone. The big size or larger size can flow down at the crystal thoroughly, and the smaller size is separate out in this. It's separate out in this fine removal that are smaller size crystal. It's maybe to recycle by dissolve again in heat exchanger and then feed into the section for that case. This is with circulating device. We have some circulating device. This look like the same. That's why we feed here and then some oxidation speed or mixer flow and circulation. That's circulation. And also this zone for solid as a product. And also the solution for overflow is maybe recycled. This is the equipment in industrial crystallizer. The most common for the industrial crystallizer, this is for the drop tube crystallizer. We have the overflow from like this, or the fine removal from like this. And this is the common use in the evaporative crystallizer and cooling crystallizer. And also for this tool, we have the external heat exchanger. This is the external heat exchanger. We use the coolant of water, the colder water, to remove the heat from the solution for cooling crystallizer. For this case, we use steam to add the heat to the crystallizer. Okay. In conclusion, for the equipment of crystallization and operation for the biological product, we can use all of this type for crystallizer equipment. The cooling crystallizer are applied for crystallization of fatty acid, lipid, marine oil, amino acid, and some organic acid. And evaporative crystallizer or vacuum crystallizer is mostly used for citric acid, organic acid, and monosodium glutamate. This is another type of glutamic acid. That's the amino acid also. And also by the small quantity of fine biochemical or specialty product, maybe crystallize using static or stirrer tank crystallizer with a surface cooling or evaporative. You can do just that. Okay, we stop this lecture now, and I will continue the crystallization for the continuous crystallizer and batch crystallizer design for the next lecture. Thank you for your attention.